Welcome to another deep dive. Today we're looking at a paper that really digs into a problem that's been getting a lot of attention in machine learning.
Mm-hmm.
It's by Nicholas Carlini and David Wagner.
Okay.
It's called Towards Evaluating the Robustness of Neural Networks.
Right.
So this paper is all about how vulnerable neural networks are to these things called adversarial examples.
Yeah, and these adversarial examples, they're not just like random noise or anything. They're like carefully crafted inputs,
Yeah.
designed to kind of exploit the specific architecture and the parameters of a neural network to make it misclassify things.
And this is a big deal, right? I mean,
Yeah.
like we're talking self-driving cars, misinterpreting road signs, or spam filters just failing.
Oh, absolutely. The stakes are huge.
Yeah.
And this paper really digs deep into how effective this one defense mechanism is called defensive distillation.
Okay.
But before we get into that, I think it's good to understand the threat model that Carlini and Wagner are talking about here.
Okay, so like what are we assuming about these adversaries?
So they're working in what's called a white box scenario,
Okay.
which means they have full knowledge of the network's architecture and parameters.
Mm-hmm.
It's like a worst case assumption, but it's super important for figuring out how strong any defense really is.
So they know exactly how the network works, and they can use that to craft these really effective attacks.
Exactly. And these attacks, they can be targeted.
Okay.
So they try to make the network misclassify something as a specific class, or they can be untargeted, where they just want to cause any misclassification at all.
Gotcha.
And the choice of target class can actually affect how difficult the attack is.
Yeah, that makes sense. Like some misclassifications are probably easier to achieve than others, just depending on the data.
Exactly. And that leads to these different attack scenarios like best case, average case, and worst case, which are all important when you're trying to really thoroughly assess robustness.
So robustness is like the key concept here.
Yeah.
When we talk about neural networks, what exactly do we mean by that?
So robustness in this context means how well a network can resist being manipulated by these adversarial examples.
Okay.
A robust network should be able to stay accurate even when it's given these carefully crafted inputs designed to fool it.
Okay, so to measure that resistance, we need ways to actually quantify the difference between, an original input and an adversarial example. This paper uses three main distance metrics: L0, L2, and L infinity.
Right.
Why those three?
Well, each one captures like a slightly different aspect of how similar or dissimilar two inputs are. So L0 is like the simplest one. It just counts the number of pixels that have been changed.
Okay.
And this is useful in situations where even changing just one pixel can make a big difference.
L2 measures the Euclidean distance. So it considers like the magnitude of changes across all the pixels.
Exactly. It gives you a more holistic view of how much distortion there is.
And then there's L infinity, which looks at the maximum change made to any single pixel.
Right. And that's important because sometimes even a small change in just one spot can really mess with the network's output.
Yeah, it's like these metrics give us a way to actually measure how subtle these attacks are.
Okay, now let's talk about this defense mechanism they're looking at, defensive distillation.
All right, so this idea actually comes from distillation, which is a technique used to compress models,
Okay.
where you have a smaller student network that learns to mimic a bigger teacher network.
So how does defensive distillation work? Is it still using a smaller student network?
Not quite. In defensive distillation, both the teacher and the student networks are the same size.
Okay.
The trick is they introduce this temperature parameter during the training process.
Yeah, I remember that. That temperature parameter changes the softmax function, right? The one that gives you the final probability for each output class.
You got it. And a higher temperature makes that probability distribution smoother. So by training the distilled model with this smoother distribution, the network might learn a more generalized understanding of the data. And that could make it less sensitive to these small changes that attackers try to introduce. And early research showed that this was actually pretty promising, right?
Yeah.
Like the attacks that people were using back then, things like the Jacobian-based saliency map attack, those weren't really working against defensively distilled networks.
Yeah, it seemed like maybe defensive distillation could be the answer to this whole adversarial example problem. But then Carlini and Wagner came along and they were like, hold on a second. Are these attacks actually strong enough to really test how robust this defense is?
So they developed new attacks to really push the limits of defensive distillation. This is where it gets interesting.
Absolutely. Their approach was really clever. They basically turned the whole problem of finding these adversarial examples into an optimization problem.
Okay, an optimization problem. So they were trying to find the most effective adversarial examples, but within certain constraints.
Precisely. They wanted to minimize the distance between the original input and the adversarial example, while also making sure that the adversarial example would be misclassified by the network.
I can see how that would make it a much stronger attack. Yeah. And they had to consider different objective functions, right, for this optimization.
Oh yeah, for sure. They experimented with different objective functions like cross-entropy loss, which measures the difference between the predicted and target probability distributions. Each objective function kind of guides the optimization process in a slightly different way.
And then there are box constraints too, right, to make sure that the adversarial examples are still valid inputs.
Definitely, you can't have pixel values that are outside of the allowed range. So they use techniques like projected gradient descent, clipped gradient descent, and change of variables to handle those constraints and make sure the adversarial example stayed within the valid input space.
Okay, so they've built this really sophisticated optimization framework for generating these adversarial examples. What happened when they tested them against these standard and defensively distilled networks?
Well, their findings were pretty significant across all these data sets like MNIST, CFAR10, and ImageNet. Their attacks worked 100% of the time on both standard and defensively distilled networks. And this was consistent across all three distance metrics, L0, L2, and L infinity.
100%.
Yeah.
So that means that defensive distillation, even though it looked promising at first, it doesn't really give us the level of robustness that we were hoping for.
It's a stark reminder that this problem is far from solved. One of their most striking findings was that they were able to fool the Inception v3 network on ImageNet just by changing the lowest bit of every single pixel.
Wow. So a change that's so small humans can't even see it. But it completely throws off this sophisticated model.
Exactly. It really shows how sensitive these deep learning approaches are to these tiny little changes. We might think of these models as intelligent and capable, but they can be tricked by things that we can't even perceive.
It makes you wonder about the nature of these models and how they're actually processing information. But the paper doesn't stop there, right? They also looked at this idea of transferability.
Yeah, transferability is a big part of this whole adversarial example problem. It's this phenomenon where adversarial examples that were made for one model can actually work on other models, even if those other models have different architectures or were trained on different data.
So even if you can secure one model, an attacker could just create adversarial examples on a different, more vulnerable model. And then transfer them over.
Exactly, and that makes it really tough to come up with good defenses. And unfortunately, Carlini and Wagner found that defensive distillation doesn't really protect against this either.
How do they test transferability with defensive distillation?
They added this confidence parameter called kappa to their attack. And by changing this parameter, they could create these high-confidence adversarial examples that were even more likely to transfer successfully to other models.
And these high-confidence examples were able to fool the defensively distilled models.
Yeah, they were. Which just goes to show that defensive distillation isn't a silver bullet. It has some serious limitations, especially when it comes to transferability.
So where does this leave us in terms of defending against adversarial examples? If defensive distillation isn't the answer, what are our options?
Well, the paper doesn't give us specific solutions, but it does make it clear that we need better defenses that can resist these sophisticated attacks and break this transferability. It's a call for more research and innovation in this area.
Yeah, this paper definitely paints a pretty sobering picture of just how vulnerable these deep learning approaches are.
It does, but it's also a really important step forward because it pushes us to explore new approaches and to develop more robust and resilient machine learning models. Yeah, it really highlights how sensitive these deep learning approaches are to even the tiniest changes. We might think of these models as intelligent and capable, but they can be tricked by things that are completely invisible to us.
Yeah, and that raises some really fundamental questions about what these models are actually doing, you know? Like, how are they processing information if they can be so easily fooled? But the paper doesn't just stop there, right? They also go into this concept of transferability.
Right, transferability, that's a huge issue. It basically means that adversarial examples that are crafted for one model can often work on other models too.
Oh, wow.
Even if those models have totally different architectures or they are trained on different data.
So even if you manage to secure one model, an attacker could just go and create adversarial examples on a different, more vulnerable model and then just transfer them over.
Exactly. It's a major challenge for creating robust defenses because it's like a moving target.
Right.
And unfortunately, Carlini and Wagner found that defensive distillation doesn't really offer much protection against this type of attack either.
So even with this temperature parameter and the smoothing, it's still vulnerable to these transferred attacks.
Yeah, it's not a foolproof solution.
How did they test transferability in the context of defensive distillation? Like, what was their approach?
Well, they introduced this thing called a confidence parameter, or kappa, into their attack.
Okay.
By tweaking this parameter, they could create these high-confidence adversarial examples that were even more likely to transfer successfully to other models.
From these high-confidence examples were basically like supercharged adversarial examples.
Kind of, you could think of it that way. They were specifically designed to be more transferable.
And did they manage to fool the defensively distilled models?
Yep, they did. They were able to successfully transfer these high-confidence adversarial examples and get the defensively distilled models to misclassify things.
Wow, so even with defensive distillation, the transferability problem still remains a major concern.
Definitely, it's a big obstacle in the quest for truly robust machine learning models.
So where does this all leave us? Like, if defensive distillation isn't the answer, what are some of the other options out there for defending against adversarial examples?
Well, the paper itself doesn't really offer any concrete solutions. It's more focused on exposing the limitations of existing defenses. But they do point out some interesting directions for future research. Like, one of the key takeaways is that we need to develop more robust defenses that can handle these sophisticated attacks and find ways to break transferability.
Yeah, I can imagine that's a pretty tough challenge given how effective these attacks are.
It's definitely not easy. Another area they highlight is the need for better distance metrics. Right now we're using these mathematical formulas like L0, L2, and L infinity, but they don't always align with how humans perceive similarity or difference.
That makes sense because we might be fooled by a small change in color that throws off a neural network, but then a larger change in shape might not have much impact on us at all.
Exactly. And those metrics wouldn't necessarily capture that nuance.
So it's like we need a distance metric that takes into account not just pixel level differences, but also the meaning of those differences.
Right. A defense mechanism based on that kind of metric could potentially be more effective at resisting these kinds of attacks.
It's a fascinating idea. It's almost like we need to incorporate some kind of human understanding into these models to make them truly robust.
Maybe that's the missing piece of the puzzle. And another thought-provoking question that the paper brings up is whether this vulnerability to adversarial examples is just an inherent limitation of the way we're currently building deep learning systems. Like, do we need to come up with fundamentally different approaches if we want to achieve real robustness?
It's a deep question. I mean, if these models can be derailed by just changing a few pixels, are we really capturing true intelligence? Or are we just scratching the surface?
That's the million-dollar question, I guess.
This deep dive has definitely been eye-opening. We started with this promising defense mechanism, defensive distillation, and then Carlini and Wagner's work really exposed its limitations.
It shows how important it is to constantly be testing and evaluating our approaches, and to not be afraid to challenge assumptions.
Yeah, and to remember that security and robustness are absolutely crucial, especially as these machine learning systems become more and more integrated into our lives.
Absolutely. We need to keep pushing for progress in this area because the stakes are just too high.
Yeah, it's a really interesting question, like, what does it actually mean for a model to be intelligent if it can be fooled by something so simple?
So where do we go from here? If defensive distillation isn't the answer, what are some of the other things researchers are looking into?
Well, Carlini and Wagner actually suggest a few directions in the paper.
Okay.
One of the big ones is developing these more robust defenses that can actually stand up to these really sophisticated attacks like the ones they were talking about.
Yeah.
Maybe it means exploring completely new defense mechanisms or finding ways to improve the ones we already have.
It seems like a pretty tough challenge, though, right? Like, these attacks are designed to exploit the very way that these neural networks learn and make decisions.
It's definitely not easy.
Yeah.
Another thing they highlight is that we need better distance metrics. The ones we're using now, like L0, L2, and L infinity, they don't always line up with how we, as humans, actually perceive similarity or difference. Right. Like we were saying before, we might be fooled by a tiny color change that completely throws off a neural network. But a much larger change in shape might not even faze us.
Exactly, and those mathematical formulas wouldn't really capture that nuance.
So are you saying we need a distance metric that takes into account not just the pixel differences, but like the actual meaning of those differences?
That's the idea. If we had a defense mechanism that was based on that kind of metric, it might be more effective at resisting these adversarial attacks.
It's like we almost need to give these models some kind of human understanding to make them truly robust.
Yeah, maybe that's the key. Another interesting question the paper raises Is this vulnerability to adversarial examples just built into the way deep learning works right now?
Hmm.
Do we need a whole new approach if we really want to achieve robustness?
Yeah, like if these models can be messed up by just changing a couple of pixels, does that mean we're really capturing intelligence?
This is a deep question.
It really is.
This whole deep dive has been pretty eye-opening. We started with this promising defense mechanism, defensive distillation, and then Carlini and Wagner's work really showed us its weaknesses.
Yeah, it's a good reminder that we need to keep testing and questioning our assumptions
Definitely.
and to always be on the lookout for new and better approaches.
Yeah.
Especially with something as important as security and robustness,
Absolutely.
especially as machine learning becomes more and more a part of our everyday lives.
The stakes are just getting higher and higher.
So this paper is really a call to action for researchers and developers
Yeah.
to keep pushing the boundaries
Yeah.
and to really prioritize robustness alongside accuracy.
It's an ongoing journey, but it's one that we need to keep taking.
Well, this has been a great discussion. Thanks for joining me on this deep dive.
It's been a pleasure.
And for all of you listening out there, keep exploring, keep questioning, and keep pushing the limits of what's possible with machine learning.